Pratima and welcome to Planet Physiology, where concepts become crystal clear. Imagine you are on a roller coaster. As it twists and turns, you instantly know whether you are moving up, down, left or right, even with your eyes closed. Ever wondered how your brain figures that out? The secret lies deep inside your inner ear, in three tiny but powerful structures called semicircular canals, your body's very own gyroscope. In our previous video, we have learned that vestibular apparatus is located in petrous part of the temporal bone. It consists of an outer bony labyrinth and inner membranous labyrinth and includes otolith organ and semicircular canals. Semicircular canals are connected to the vestibule at both ends and are filled with endolymph. There are three semicircular canals in each ear: anterior or superior, posterior and lateral or horizontal. They are positioned at right angles to each other, just like X, Y and Z axis in 3D space. The anterior and posterior canals are oriented vertically at right angles to each other. Anterior canal runs forwards while posterior canal runs backwards. When head is flexed by 30 degrees, the lateral canal lies in a horizontal plane. This arrangement, three canals at right angles, allows detection of head rotation in any plane. Let's understand this with example. Horizontal canal detects head rotation around the vertical axis, that is, in the transverse or horizontal plane. Examples include side-to-side head movements when nodding no, the spinning motion of an ice skater or gymnast or dancer, or simply rotating in an office chair. The anterior canal detects rotation around the lateral axis, that is, in the sagittal plane, and its example includes nodding yes or performing forward or backward flips in gymnastics or during dance. Posterior canal detects rotation around the sagittal axis, that is in the coronal plane, like tilting the head so that ear moves towards the shoulder, or doing a cartwheel or a side flip in acrobatics or dance. Now let's take a closer look at the semicircular canals. One end of each canal widens into a dilated region called ampulla. Inside each ampulla lies a small elevation called as crista ampullaris, which is the receptor organ for detecting head rotation. The crista consists of sensory epithelium made up of hair cells and supporting cells. On the top of crista sits a gelatinous mass called cupula, which projects into the lumen of the canal and nearly touches the opposite wall of the ampulla. In doing so, cupula divides the ampulla into two compartments. The cilia of hair cells are embedded in this cupula. Vestibular nerve fibers form synaptic connections with the bases and the sides of the hair cells. Even at rest, vestibular nerve fires about 100 impulses per second. Hair cells in each canal are arranged in polarized manner. In horizontal canals, the kinocilia of hair cells are oriented towards the utricle, while in anterior and posterior canals, they are oriented away from the utricle. When the stereocilia bend towards the kinocilium, hair cells get depolarized and increases the firing rate of the vestibular nerve. When they bend away from the kinocilium, hair cells are inhibited, decreasing the firing rate. Okay, this was about the structure of semicircular canal. And before we move to their functions, it's important to note that semicircular canals of both ears work in functional pairs. The horizontal canals of right and the left ears form one pair. The anterior canal of one ear and the posterior canal of the other ear are almost parallel, forming other two functional pairs. During any rotational movement, when one canal in a pair is excited, its partner on the other side is inhibited. This mechanism increases accuracy and helps the brain determine the precise direction and speed of rotation. With this understanding of semicircular canals, let's now discuss the functions. The first is role of semicircular canals in detection of head rotation or angular acceleration. This is also known as role in dynamic equilibrium. When the head and the body are in normal erect position, cupula in each semicircular canal is at rest. In this state, the vestibular nerves fire at a baseline rate which is about 100 impulses per second as shown in this image. Because the three canals are oriented in three different planes, rotation of head in any direction is immediately detected by one of the pairs of the semicircular canals. Let's take the case of a person turning head to the right in horizontal plane, the job of horizontal canals. This is the diagrammatic representation of horizontal canals in resting position. The cupulas of both the canals are oriented vertically and kynocelia of their hair cells are facing towards the utricle. At this point, vestibular nerves on both the sides are firing at the baseline rate as shown in the lower part of the picture. As the head begins to rotate to the right, the bony canals also move to the right. However, endolymph inside lags behind due to its inertia, causing bending of the cupula to the left. In the right canal, this bending moves the stereocilia towards the kynocelia, exciting the hair cells and increasing the impulse frequency. In contrast, in the left canal, the stereocilia bend away from the kynocelia, inhibiting the hair cells and decreasing the impulse frequency. The brain compares these two opposite signals and instantly identifies that the head is turning to the right. If the head continues to rotate at a constant speed, within about 25 to 30 seconds, the endolymph overcomes the inertia and starts moving along with the canals, that is, to the right. This returns the cupula back to its resting position and the firing rates in both the vestibular nerves return to the baseline. Now this continues as long as head rotation continues at the same velocity. When head rotation stops suddenly, the bony canals also stop immediately. But again, the endolymph keeps moving due to its inertia. Now this time, because of this endolymph movement, the cupula turns to the right. Now, in the right canal, hair cells are inhibited and in the left canal, hair cells are excited. I believe you understood why. If not, observe the direction of the movement of stereocilia with respect to kynocelium. Okay. The brain interprets this pattern of signals as rotation to the right has stopped. Within few seconds, the endolymph also stops moving and cupula returns to the rest and hair cell discharge also returns to the baseline level. Thus, semicircular canals detect changes only at the beginning and at the end of rotation, that is, the start and the stop, but not the steady unchanging motions. Now let's move to the second function of semicircular canal, its predictive role in maintaining equilibrium. During rapidly changing body movements, semicircular canals work like early warning sensors. They predict that the loss of balance, that is mal-equilibrium, is about to happen even before actually you start to wobble. The signals from the canals travel to the cerebellum, which then makes quick adjustments in the muscle tone to keep you steady. That's why even during complex three-dimensional movements like dancing, playing sports or skating, you usually maintain your balance. Okay, the next function is role of semicircular canals in vestibulo-ocular reflex. This is your image stabilizer system. It keeps your gaze fixed on an object even when the head is moving. Without it, the world would look like a shaky camera video every time you turn your head. So here's how it works. The semicircular canals detect head rotation and send signals to the vestibular nuclei. They in turn transmit signals via medial longitudinal fasciculus to the extraocular muscles to move your eyes in equal and opposite direction to that of head rotation. This reflex is super quick. The latency is only about 12 milliseconds. So thanks to VOR, you can read the signboards while jogging or see clearly while sitting in a moving vehicle. Okay, but if head rotation goes beyond 60 degrees, the eyes make a rapid movement in the same direction as that of head to fix the gaze on new object. Thus, VOR, that is vestibulo-ocular reflex, also gives rise to nystagmus. Now let's move on to the clinical aspects when semicircular canals go wrong. If canals don't work properly, you may experience vertigo, nystagmus and balancing issues, especially with the rotational movements. Motion sickness is a common example, and here excessive stimulation of vestibular system or conflicting information from the vestibular and the visual systems cause symptoms like palpitation, nausea, sweating and vomiting. Many people experience motion sickness while reading in a moving car or sensitive individuals while riding in a bus, train or ship. The symptoms are probably due to reflexes mediated via vestibular connections in the brainstem and the flocculonodular lobe of the cerebellum. In this case, vestibular suppressants are helpful to prevent or relieve these sensations. Okay, have you heard of space motion sickness, where nausea, vomiting, vertigo is experienced by astronauts? Think about why and drop your answers in the comments. Now coming to another clinical aspect related with semicircular canals, benign paroxysmal positional vertigo. Here the autoconia from the utricle get into the semicircular canal, triggering dizziness with certain head movements. We have already discussed this in detail in earlier video on otolith organs. Link is in the description below. Okay, so what are the important takeaways of this session? Anterior, posterior and lateral semicircular canals are oriented at right angles to each other to detect head rotation in any of the planes. Each canal ends in an ampulla which has crista containing hair cells. Their cilia are embedded in the cupula, the gelatinous mass. Bending of stereocilia towards the kinocilium excites the hair cells and bending away inhibits them. Semicircular canals are specialized to detect angular acceleration, that is the rotational movement in any plane. Their predictive function helps to maintain balance during rapid movements, and because of VOR, they help in vision stabilization during the movement. So next time you spin, flip or turn your head, remember your semicircular canals are working in precise pairs, giving your brain real-time updates on your movements. Thank you for watching and see you in the next part, where we shall explore the connections and functions of the entire vestibular system. If you enjoy my presentations, press the like button and share it with your friends. For more such videos, subscribe my channel and click the bell icon. Thank you for watching and see you in the next video.